Welcome. In this video, we will be taking a look at section 3.8, and we'll be looking at improper integrals. Our objective today is, again, just to evaluate these improper integrals. And let's take a look at our first couple definitions here. So we're going to be considering when a improper integral is going to converge or diverge. So the convergence of an improper integral, the first definition says that we have an integral in the form of the integral from a to infinity of f of x dx converges if the limit as t approaches infinity of the integral of a to t of f of x dx exists and is a finite number. So if the limit goes to positive infinity or negative infinity, in other words, if we have infinite amount of area underneath the curve on that interval, then the integral is said to diverge. So we have some notation there to go along with that on the bottom there. So here is our, again, integral from a to infinity, and we can replace that with the limit as t goes to infinity for the integral a to t. Now, we can also consider what if we have a lower limit that is going to negative infinity. We'll have a similar definition here, a integral in the form of the integral of from negative infinity to b of f of x dx converges if the limit as t goes to negative infinity for the integral going from b or t to b of f of x dx exists and is finite if it is a finite number. So when we consider, again, if the limit goes to positive or negative infinity, again, we would say that that integral would diverge. And so we have very similar notation here. If we let the t go to infinity, we'll have the limit as t goes to infinity or to negative infinity of the integral from t to b. And we want to make sure that that, again, converges to a finite number. So before we get into the actual integrals that we'll take a look at in the lesson, let's go ahead and just remind ourselves of some limit properties and some smaller limits as x goes to infinity. So the first example A, we have the limit as x goes to infinity of 1 over x. So when we consider the function 1 over x, we can imagine that shape of the function. And the shape of 1 over x, well, it's got an intercept, a y-intercept, x equals 0 is undefined. But let's just consider the positive values for that. As x increases, the fraction here, or this ratio, is decreasing. So we'll have kind of this kind of shape for those positive values of x. And so you can notice that as x increases without bound, this function is, or ratio is tending to 0. And so this limit here, we would say, goes to 0. We can then consider, well, what about if we consider the same limit as x goes to 0 plus, or 0 from the positive or from the right? So this would be approaching 0 from the right. Well, again, we could use that little graph that we created here as we approach from the positive end of our graph. It looks like this function, again, is going to increase without bound. And so this would eventually go to positive infinity. We'll shoot off to that positive infinity. Let's take a look at this second grouping where we have the exponential function. Now, part C, we want to take the limit as x goes to infinity of e raised to the negative x power. let's just recall here that this limit would be equivalent to the limit as x goes to infinity of 1 divided by e to the x. Because we have that negative exponent, negative x, we can really rewrite that exponential in the denominator. And since e to the x, it's an increasing function, we know that as x increases to infinity, e to the x will also increase off to infinity. And so we have a very similar situation to part A. We have a function going to infinity in the denominator. And so this e to the x going towards infinity will actually force that ratio down to 0. So this limit here we'd also have going to 0. So e to the x grows much, much faster, obviously, than that constant 1. And so we go off to infinity, or off to 0 there. So the last limit we can take a look at, the limit as x approaches infinity of e to the x. Well, again, here we can say, well, e to the x itself is just an increasing function. We can even draw that exponential function. X equals 0, we're going to be equal to 1. We'll have exponential growth to the right. So it'll look something like that. And as x increases without bound, again, e to the x will increase without bound. Those y values will shoot off to infinity. So we can say that as the limit as x approaches infinity of e to the x, that'll go off to infinity for us. So those are just some reminders of kind of our limits at infinity. Those will be useful for when we jump into these improper integrals. So let's look at a few of the examples here, and then we'll save a few for the second part of this video. So we want to evaluate the following improper integrals. And so let's go ahead and jump into letter A. So letter A, we have the integral from 1 to infinity of 1 over x squared dx. So again, we can't evaluate this limit with the bound at infinity right now. But we can consider what happens as this value approaches, this upper bound approaches infinity. So we can write the following. We can say, what's the limit as, if this is my upper bound, I could call that little b here. And I want little b to approach infinity. We're going to consider the integral from 1 to b of that same function. And we could rewrite this function 1 over x squared as x to the negative 2 dx. So we're considering, again, replacing that upper bound with a dummy variable b and letting that variable b tend off towards infinity. Okay, so now that we have this setup, we can go ahead and consider our integral. So I'm going to rewrite my limit statement. Limit as b goes to infinity. And then we will then consider our antiderivative. We can say that this is x raised to the negative first power. We'll add 1 to that exponent and divide by 1, which is really multiplying by 1, same idea here. So negative x raised to the negative 1. And we'll go ahead and evaluate this expression from 1 to b. Again, let's go ahead and rewrite our limit statement, and then we'll evaluate our expression. So we have limit as b goes to infinity. Here we have negative. Really, x to the negative 1 is 1 over x here. So that's the function we're working with, negative 1 over x. And we'd like to evaluate that at b and at 1. So we can say that's negative 1 over b minus negative 1 over 1. We can end that parenthesis there. And let's go ahead and continue with this a little bit more. Notice that we have a couple double negatives here, so we can go ahead and make that a positive 1. And we'll also notice that when we evaluate this limit, we could say that as the limit as b approaches infinity, this value right here, -1 over b, as b approaches infinity, that is going to just converge to 0. So this value here, again, converges to 0. We have that double negative, and we just have really a 1 here, 1 over 1. And so this limit actually ends up just being 0 plus 1, or it'll converge to 1. So this is really interesting if we pause to just take a moment of what we've done here. This 1 over x squared function on its positive axis, again, when x is equal to 1, this function is equal to 1. And it's undefined at 0, so at 1 we're equal to 1. And again, as x increases, this ratio 1 over x squared will decrease without bounds. So we'll decrease down to 0. So this function, we can imagine, kind of looks like this, very similar to maybe a negative exponential in shape. Again, as x increases, will decrease without bound. And we're considering here, what is the area underneath this curve from x equals 1 all the way towards infinity? So we're going forever to that right. And in fact, this area that we're creating here, it's really, really small here and towards 0. As we, again, continue off the page, this is areas, function's going to continue to the right, and our area is going to, again, keep picking up to the right. This actually is a finite area, which is quite amazing if we kind of think about that geometrically, that this area is going to converge to 1 unit of area. So a pretty wild result for what we call kind of an unbounded integral here. It's going off to infinity. It's a pretty cool result, I think, to just consider what's done there. So let's go ahead and take a look at part B. We have our first exponential problem, and we're going to take a look at the integral from 1 to infinity of the exponential e raised to the negative x. So again, we'll have kind of a similar treatment to this upper bound infinity. We can say that this is equivalent to the limit as b goes to positive infinity of the integral from 1 to b of e raised to the negative x dx. Now we can, again, approach our integral here. So e raised to the negative x, well, this is an exponential function. And so we can first consider its antiderivative as e raised to the negative x. Again, we can add this limit portion in. So we have the limit as b goes to infinity of, we'll have e raised to the negative x, but notice that we have a negative in that exponent, so we can't leave it there. The derivative of that exponent is -1, and so in terms of our antiderivative, instead of multiplying by -1, we divide by that -1, but the change is equivalent. We'd still get negative e raised to the negative x for that antiderivative, and we want to evaluate that from 1 to b. So that would be our antiderivative expression. So if we wanted to rewrite this, we could say that this is the limit as b goes to infinity. And we'll have our function. This is really going to be -1 over e raised to the x power. So this is negative 1 over e to the x as our function. But, again, we're evaluating this from b to 1, so we can say that's e to the b minus negative 1 over e to the first power. We'll follow that with a closed parentheses. So again, let's notice what happens with this limit as b goes to infinity. If we have e raised to the b, or e raised to infinity in this case, down below, well, that part of the function, that denominator, is tending to infinity. And so negative 1 over infinity, well, that value is, again, tending off towards 0 again. So we have this first chunk that will go to 0. We'll have another double negative value here, so subtracting a negative will make a positive. And then 1 over e is, again, just a constant for us. There's no variables there. So when we evaluate, we'll just have really 0 plus 1 over e, which will just give us that 1 over e value. So that would be another converging integral. It is a finite number here, and so we would say that this converges. And we would also say that that previous one converges, so I can add that in there. So we can say it converges as well. So that converges too. All right, let's take a look at a couple more. We'll take a look at part C. All right, in this question we have the integral from 1 to infinity of 3 divided by x raised to the 0.8 dx. Okay, so let's see. I might even rewrite this one time before I introduce that limit. We have the integral from 1 to infinity. We could rewrite this as 3 and then x raised to the negative 0.8 dx. That will kind of prepare that for an antiderivative here that we're going to need to take. So we can say that this is the limit as, we'll again say that b is tending off towards infinity. Then the integral is 1 to b, 3x raised to the negative 0.8 dx. All right, so let's go ahead and consider that antiderivative. We'll keep that limit intact here. This is limit from b to infinity. And then we'll consider our antiderivative. That looks like 3 is going to stay as a constant. We want to add 1 to the exponent, so x raised to the negative 0.8 will become 0.2 if we add 1. And then we'll subtract, or divide, excuse me, by 0.2. All of this we're going to want to consider evaluating from b, or 1 to b. We'll do that in the next step. We can clean this up just a little bit. If we have 3 divided by 0.2, we can move our decimal over once in the denominator and once in the numerator. We'll make that 30. And then 30 divided by 2 is really 15. So if you prefer, we could write that as 15 x raised to the 0.2. Just to clean that up just a little bit. And we'll have the limit from as b goes to infinity. And we'll evaluate 15, and then x raised to the 0.2, we'll do our first endpoint of b, so that would be b raised to the 0.2, and then subtract 15, and then 1 raised to the 0.2. We can end that parenthesis together. Okay, Now let's go ahead and consider what happens to this expression as b goes to infinity. So as b goes to infinity, we're taking a look at this component right here. Well, if a number is raised to 0.2, again, this is kind of similar to something like a square root function, but it's not quite there. It's 0.2 is not a half, but it's the same kind of type. It's still a decimal. 0.5 would be a square root, but this is a little bit lower. The point is here is if we put larger and larger values in for b here, that value, b raised to the 0.2, is going to be an increasing function. So this is increasing. And so since that's increasing, as b goes to infinity, that term as well will tend off towards infinity. So what we have here is some term that tends off towards infinity, and then subtracting some constant term. Again, when a constant term is subtracted from infinity, we're still going to get a very, very large number tending off towards infinity. So that's not going to affect that first value tending off towards infinity. So this, we would conclude that this would actually diverge off to positive infinity. So this would be our first diverging integral. So this diverges off to positive infinity, which means, what does this mean for us? That this integral, or the area underneath this function from 0 to infinity, has infinite amount of area as that upper bound ranges to infinity. So there's not a finite amount of area underneath that function. There's actually infinite amount of area over that function. Let's go ahead and try an exponential function to finish up this part of the video. We have the integral from negative infinity to 2 of the exponential e to the x dx. So here we're considering what happens if we open up this lower bound to negative infinity. So let's consider now how we could rewrite this integral. Now we want to consider, well, what happens, again, when this lower bound, a, tends off to infinity. So we'll write this as the limit as a goes off to infinity, or excuse me, negative infinity here. And we'll consider the integral from a to 2. So our upper bound is 2, our lower bound is now a. Now we want to have the integral of e raised to the x dx, which in itself is an integral that has its own antiderivative. So e to the x stays intact as its own antiderivative. So we could say this is the limit as a goes to negative infinity of, we have e to the x as our antiderivative, and we want to evaluate this at 2 and at a. Now let's go ahead and work out this evaluation. We have the limit as a goes to negative infinity of e raised to the second power subtract e raised to the a power for those two bounds. And again, now let's go ahead and consider what this will work out with when we evaluate a as it goes to negative infinity. So if we evaluate a here at negative infinity, well, e raised to negative infinity, again, that's equivalent to 1 over e raised to infinity. And we know e raised to infinity goes to infinity. And so this expression 1 over e raised to infinity will actually tend off towards 0. So this value, the second term here, will actually in total go off to infinite 0. And we'll just be left with that first term, which is e raised to the second power. So when this is evaluated all the way, we can say that this is going to be e raised to the 2. That's constant. Subtract 0, and that's just going to be itself e raised to the second power. So this one, we'd say that that converges. This converges, and it converges with e squared area, which is, again, pretty mind-blowing when you think about e squared area. That's a very specific number that we're using in calculus, and that would be the area for that function from negative infinity to 2. So thanks for watching this first part. You can take a look at the second part of this video where we'll go through a few more examples in this lesson. So see you in the next video.